Okay, let's get started. We still have missing a couple of students. Let me actually send out a notice for them, okay? Kingston, Harris. Still missing Leo. Let me send out notice to him. Okay, he's in. Okay, let's get started. Everybody hear me?
Yeah.
Okay. So today we are going to work on the Boolean algebra. Last time we talked about if then else, the selection structure, and today we are focused on Boolean algebra. So Boolean algebra, we focus on if we have an if parenthesis. Here you put a Boolean value right here, right? And then you have a while loop. You while something here also a Boolean value, true or false, right here. If we do for loop you have integer I equals 0. And then right here it's a Boolean condition. Second one is a Boolean condition. So put a Boolean over here. Okay, so today we are focused on these different Boolean conditions. Okay, how we can work on them. Okay, and how to actually design them. Okay, this is the main idea of what we are doing here. So we are actually trying to understand what is Boolean expression and comparing the Boolean expression and how to do simplification for it. So basically, we are going to talk about Boolean algebra and proof of the Boolean theorems and doing logic design, how to design logic based on each different Boolean algebra. And then the compound conditions, and then the calendar year project. Okay, these are different topics we will cover today. So first one, let's talk about Boolean algebra. Okay, Boolean algebra. So before we go into the Boolean algebra, we need to know about Boolean. Okay, we need to talk about what is Boolean. Boolean is Mr. Boole's math. Okay, this Boole is the last name. an become adjective or possessive term. So an is making it a adjective. So who is Mr. Boole? Okay, Mr. Boole. So you go to internet, you search for this person called George Boole. Okay, they pop up a George Boole, and this George Boole is a person in England. Okay, and then he was born in 1815, died in 1864. So just age 49, he passed away. And then we know that Abraham Lincoln is born in 1809 and died at 1865. So basically, he's about the same time of the President Lincoln. Okay, about the same time. They kind of have large overlap in their life. So this person, George Boole, actually invented this Boolean algebra. So there's Boolean algebra, Boolean expression theory, Boolean function, Boolean inequality, Boolean polynomial, Boolean rules. These different kind of the Boolean things are based on him. So he actually is a foundation of computer programming. So if we talk about Isaac Newton, F equals ma in physics, then this Mr. Boole Mr. Boole's 0, 1, the binary Boolean algebra is the same value in computer science. Okay, it's actually he's doing the most important work in computer science. So this Boolean algebra is pretty important. Okay, our modern day computer logic is basically based on this so-called Boolean algebra. So whatever here, this website introduce who he is and how he actually become a mathematician and his major contributions. So here we don't go over his story. We actually will focus on Boolean algebra. Okay. So Boolean is using his name. So first we know that Boolean is based on 0 and 1, true and false. Okay. So now let's look at the regular algebra. So everyone in high school will learn algebra. And then in college, you may know that there's a course called linear algebra. And right here, we are talking about Boolean algebra. Okay, now, so what is really is algebra? Okay, let me ask a couple of the ninth graders, eighth graders about algebra. You may be working on algebra 1. So let me ask Kirsten, what is algebra? Kirsten, hear me?
It's like mathematics, but you use symbols or other things to represent unknown values.
So you use x, y to represent unknown value.
Yeah.
Other than that, what do you know? What do you know about algebra? Other than this, what do you know about algebra? So in the elementary school, okay, K to 6, you learn arithmetic. So arithmetic, you basically learning 1 plus 2 plus 1/2, something like that. Okay, whatever plus minus, you learn plus minus multiply division. Okay, that's called arithmetic. So algebra, you introduce the idea of x, y into there. Other than that, what do you learn about algebra, Kirsten? What else do you learn about algebra?
How to manipulate the numbers or
Yeah,
how
that's arithmetic. How about Qian? How do you know about algebra?
Uh, I think I don't know the exact definition, but I make signs to calculate the value that I want to get.
You still do calculations, you still talk about arithmetic. How about Harrison? What's your view about algebra?
Uh, it's used to like separate like values from like one another.
I don't get it. I don't get what you are talking about. Can you repeat again? Whatever view, can you rephrase it? Use different word to talk about algebra.
Like to separate like one like value from like the rest to like solve for it.
Separate what?
Separate a value from like the rest.
The rest of what?
Rest of like the equation.
Are we doing that in algebra? I don't get it, okay? So, I mean, I think in a way, what John said and what Kirsten said is closer. How about Stephen? What's your view about algebra?
You solve for unknown variables.
Algebra has nothing to do with software. Can you redo it, refresh it again?
Um, I don't really know.
You don't know. How about
Yeah.
Belinda?
I could only think of what Kingston and Gian already said.
Okay. How about Leo? Do you have any other view?
Define function and make some
Okay, talk about function, define function. We'll talk about function later, okay? But function related to algebra, yes. And then
remember there's like exponents or like a log maybe.
exponent or log. The exponent or log are different kind of function, but you do not talk about the real essence of algebra. You are still talking about something algebra can do, but not talking about algebra itself. Okay, anyway, look like everyone's view about algebra is very weak. So in a way, you are learning arithmetic in elementary school, K to 6. Okay, you may start to learn about algebra from 7th grade to 12th grade. Okay, some of you may finish in 9th grade, 10th grade. You study to do calculus. Then the next level, you go to calculus. Okay, these three terms are totally different things. Okay, we talk about arithmetic, algebra, and calculus. These are actually of different meaning. So arithmetic, you talk about you have 1 plus 2 divided by 4, whatever. These are actually talking about plus, minus, division, multiply, modular. These are different kind of arithmetic. Okay, you give them numbers and you do operation on it. That's correct. Algebra, you involve x, y, z, maybe also 1, 2, 3, maybe also 4.4, whatever. So you may have x equals 4.4 plus y, something like that. So basically, you introduce the unknown variable, yes. You introduce the unknown variable, and arithmetic do not have the unknown variable. So here you introduce the unknown variables, but you looking into the structure of the computation. So when you have x equals y plus 1, no matter what x is, y is, they will form a relationship of x and y. I'm sorry, plus 1 is this one, okay. So you form a mathematical relationship of this line, and this line actually is the x equals y plus 1. So you are exploring the mathematical structure. No matter what x is, y is, this rule always be valid. So we are talking about the relationship of two variables. And arithmetic do not involve the relationship of two variables because arithmetic no variable at all. Okay, and in advance, you can also say that, okay, you may have a function, f of x equals x plus 1, and you define it as y, okay. So this actually form a line right here. It actually y equals f of x equals x plus 1. So that line form another relationship. So function also is a kind of a mathematical term like you can put into the algebra. As long as the algebra law holds, then the computational relationship is valid. Okay, no matter what x, y is or what f of x is, the algebraic relationship should be the same. Now we call it algebra. Okay, so now let's look into the Boolean algebra. So these are algebra. Algebra talking about when you define a variable x, y, and then x, y always holding a certain relationship those kind of mathematical relationship and computational structure, we call it algebra. So we talk about algebra of first degree relationship, linear relationship, f of x equals x plus 1, that's a linear relationship. We talk about quadratic relationship. Okay, quadratic relationship. We talk about polynomial relationship. Okay, different relationship, that's a different kind of algebra. So we have first order equation, second order equation, third order equation, different kind of equations. So these are talking about any y equals x squared plus x plus 1. This is the relationship between a x and a y, a independent variable versus a dependent variable. And the mathematical structure that related to it is called algebra. Okay. Now, next one is actually calculus. Calculus is different story. Calculus talking about the relationship of functions. So we say df of x dx, that you try to find the function of the derivative. So let's assume that x squares the derivative will be equals to x. That's actually y. Okay, let's assume that this is the relation. So you are talking about a function and trying to find the derivative of it, and trying to find the integral of the function. So calculus talking about integral and the derivative is different from algebra. Algebra only talking about the variables relationship. Calculus moving on to the next level is actually talking about the integral and the derivative of the function. But this actually calculus would based on algebra, and algebra based on the arithmetic. Okay, these are the relationship like that. So you learn math, you actually will explore different kind of mathematical structure and then learn more of the relationship about how to deal with the number functions and geometry. Okay, these are the relationship. Now let's go back to the Boolean algebra. So regular algebra, the algebra 1, algebra 2, you're talking about you have 1, 2.2. Okay, the integer and real numbers, and you talk about y equals x plus 1. These are the relationship of defining in the real domain, okay, real numbers. So your x belonging to real domain. That's called algebra. And then when we talk about Boolean algebra, so Boolean algebra is talking about a Boolean variable b that belonging to a 0 or 1, true or false. The only two value, but these two value also hold y equals x and true. This relationship using a variable defining in the Boolean domain, we call it Boolean algebra. Okay, and then when you look into a metric, okay, a metric of equals to 1, 2, 0, 0, okay, and then you actually have the so-called mx plus t equals y. Y is a vector, x is a vector, m is a metric, t is a vector. So something like that, working on a arithmetic relationship of a matrix and vectors of multi-directional. This one we call it linear algebra. It's a college topic. We call it linear algebra. So linear algebra is an algebra operating on linear system. Boolean algebra is a algebra operating on Boolean domain. Regular algebra is an algebra operating on real numbers or complex numbers. Is that okay so far?
Yeah.
Okay, so basically we are going to look into the rules of the operations that define on 0 and 1 only. So the rule is different from your linear algebra. These two are not the same. It's called algebra, Boolean algebra, but that's just because we want to look into the computational structure of the Boolean algebra. It is not the same as the so-called regular algebra. It is also not the same as linear algebra. When you look into the linear algebra's rule also different from the rule in the regular algebra because it's operating on a metric, operating on a vector. So there are some specialty in there as well, okay? So that's what we want to say, that actually we are going to study the Boolean expression, Boolean logic, Boolean values, and how they actually can be operated in the Boolean algebra. So it's a special topic. Okay, in UC Irvine has an ICS 6B course. It's completely on Boolean algebra. Okay. Not every university teaches Boolean algebra as a separate course, but Irvine has that course. Okay. Okay, now, so it's very obvious that we want to learn Boolean expressions so that we can manipulate them, and also we can simplify them. That's the main purpose. One is to manipulate the Boolean logic. The other way is to simplify it. Okay, so we can do design and we can understand the program. Okay, so there are a set of rules formulated by English mathematician George Boole to describe these different propositions. Okay, so basically he's the person who set up the foundations for Boolean algebras. So we may have two values, true or false. So right here, sometimes we write 1, sometimes we write 2, it's the same thing. Okay, sometimes we write 0 and we write false, it's the same thing. Okay. So true or false, we call it Boolean value. Usually 1 and 0, we call it the Boolean algebra. Okay. And then, okay, let's actually use a slice, use the whiteboard. So the Boolean value, you have 0 or 1. Okay, Boolean value, Boolean. Boolean value, you have 0 or 1, okay? And sometimes we call it false and true, okay? And then you may have Boolean logic, you have and or not. These 3 major Boolean operators. So not, we write it as exclamation mark or double, okay, and then end is double ampersand, okay. And we also have another one called bitwise and or. This one is simple and this one is, okay. And then there's another logic called inclusive or, that's actually a cap sign, okay. Okay, in AP level, we actually need to only look at this, okay. These 2 are not tested. But some of the homework you may see this inclusive or, but it's okay. You also need to learn it. Okay, so these are the Boolean logic function, and then in Java we write in this way. So these 2 are Java way, okay, Java way. And then in Boolean algebra, this is Boolean algebra's way to write. Okay, and we use a dot or multiply, or we use plus. Not we use a minus sign. Okay, these are Boolean algebra way of writing it. Okay, need to remember that. Java's notation is Java notation, and Boolean algebra, we use a mathematical term. So we use a 0, 1, multiply, plus, minus. Okay, it's different symbols for it. So Boolean algebra's main purpose is to study the theorems. Theorem is something that always true when we explore the Boolean algebra's computational structures. Okay, so these are the most important rules. We call it as basic 7 Boolean postulates. Okay, postulates. So rule number 1 is actually a variable x is either equals 0 or equals 1. There's no something like x equals 0.5 or x equals 1 by 30%, 0 by 70%. There's no such thing like that, okay? So when we talk about 0 or 1, Boolean algebra is actually always 0 or is always 1. It's either way, okay? And when you actually have 1 30% and then 0 70%, these are quantum logic, okay? Quantum logic is different. But that's not regular logic, okay? Quantum logic may have that, but that's not what we are talking about right here, okay? So no probability involved. It's actually either true or false. There's no way, no anything in between. That's rule number 1. Rule number 2, 0 and the 0 is 0. 1 or 1 is 1. 0 or 0 is 0. 1 and the 1 is 1. Okay, these are basic rule you need to remember. Okay, true or false. 0 is false. 1 is true. Okay. 1 and the 0 is 0. 0 and the 1 is 0. 1 or 0 is 1. 1 or 1 is 1. Okay, so these are very easy to understand except for this rule. Any other rule is the same as math. Okay, the same as math. Only the additive rule, 1 plus 1 not equals 2. Okay, we don't have 2 in here. It's actually 1 plus 1 equals 1. Other than that, Boolean structure is the same as arithmetic structure. Is that okay?
Yeah.
So sometimes we use this advantage to simplify the logic. Okay, simplify the logic. Okay, so these are the basic 7 Boolean postulates. Now, next one, we are going to talk about the basic rules and we are going to prove that. Okay, we'll prove that. And then there is a rule called duality. We'll talk about duality later. Okay, but you remember that end is either multiplied or a single dot. Sometimes the dot can be also be omitted. Okay, sometimes it can also be omitted, and or is plus sign. Okay, anyway, let's look at the other rule. Based on that 7 basic postulates. Next one, you need to look at commutative law. Okay, commutative law. Let's look at T1. So when you look at this Boolean algebra, you can use truth table to prove it. You can also use a Venn diagram to prove it. Okay, but you need to know both of these, okay, when you need to prove them. Okay, so first let's look at a Venn diagram. Venn diagram means that, okay, when you have a set of A, outside of A, we call it not A. It's okay? Anything outside is called not A. Okay, let's assume that we have a number that's actually a set of 1, 2, 3. That's A set. So not A set means that any integer are not 1, 2, 3 is in not A set. Okay, so remember that. Okay. So here you have A plus B equals B plus A. So your A set is right here. Your B set is right here. So your A plus B is this whole thing. A or B is this whole thing. B plus A is also this whole thing. So basically, this do a whole, okay, by Venn diagram is very clear. Next one, AB equals BA is actually A set intersect with B set. We are talking about this portion. So this time means the intersection. Time means actually, but this time symbol, the multiply and that being omitted right here. So you actually see the same is AB equal BA. So basically, plus sign and the multiply sign in Boolean algebra, you move the order of the operand. It doesn't matter. Okay, A or B or B or A is the same thing. A and B or B and A is the same thing. Okay, and then next one. A and the B and the C and the C and the B and the A it actually will also be the same thing. This won't create trouble. Okay. Next one, associative term. So A plus B plus C. You all disperse or you all disperse is the same. Okay, because A or B or C, A or B or C is the whole thing right here. No matter who or with who, it doesn't matter. A and the B and the C is the same thing. It's only this small portion that everyone actually are in. So it actually is still the same. Okay. Any questions so far?
No.
No? Next one is more tricky, okay? Especially the B rule is more tricky. Okay. The distribute rule is, I think, is okay because it's the same as math. So A and B or C, A and B or C. Let's look at B or C. B or C is right here. This is B or C. Okay, this is B or C. A and B or C is this part. Okay, A and B or C, this part. Let's look at the right-hand side, AB and AC. AB or AC. AB is this portion. AC is this portion. So you can see that these two are the same. A and the B or C and equivalent to AB or AC. These two are the same. Is that okay? So you can multiply to each element that's the same as your multiplication rules. Okay?
Okay.
B rule is more bizarre. B rule is not the same as algebra because B rule usually A plus BC is A plus BC in algebra, but you cannot do A plus B and A plus C. But this Boolean algebra, this will hold. This actually in Boolean algebra is okay. It's different from regular algebra. So this rule you must remember. When you distribute a plus sign into each element, that's still true. Okay. So A or BC. Okay, let's look at this one. So let's do it here. A, B, C. So B and C is this portion. A or B and C is A or B and C. This is the A or B and C, okay? The other one is actually you distribute it to each individual one. It should be A or B and A or C. Okay, let's look at it. This one. This one you have A right here, you have B right here, you have C right here. So your A or B is this portion. A or B is this portion. A or C, let's use different color. A or C is this portion. Okay, so the green one and yellow ones intersect. Green one and yellow ones intersect is right here. It's actually the same as the red circle. Is okay?
Yeah.
Yeah.
So basically, after class, you need to draw this Venn diagram by yourself, making sure you understand. After you understand, you must remember that's distributed law. You need to remember it. A and B or C equal to AB or AC. Okay. A or B and C equals A or B and A or C. Okay, these are this distribution law. Next one, identity law. Identity law is simple. Okay, A or A equals A. Okay, yourself or yourself is yourself. That's easy. A and A equals A. Yourself and yourself is yourself. Actually, these are overlap, so this one is easy. Number 5, let's have A, B, or AB bar equals A. So A, B, okay. AB, when you have AB, it means that in A and in B. In A and in B is this part. In A and in B is this part. This one in A but not in B. In A not in B is this part. So AB plus AB bar is actually equals A. Okay, so this one actually equivalent to A B plus B bar. And B plus B bar is 1. So A and 1 equals A. So by derivative, you still can derive the equation to be the same. By Venn diagram, you can see it as well. Any question?
What? I don't quite get what the bar means.
Bar means not, or we already talking about it in the beginning.
Sorry, my Wi-Fi was like very choppy. I didn't hear.
Bar means not. At the first minute, we talk about A set is right here. A bar is outside. Anything outside of A is A bar. That's the first thing we talk about. Any other question? The first thing we talk about is there is a set 1, 2, 3. Any number not 1, 2, 3 is A bar. Any integer but not 1, 2, 3. We talk about this already. You have to pay attention. That's called A bar. So you have a set A, outside is A bar. You have a B, so B is right here, and B bar means anything not inside B, that's actually a B bar. So this portion is A and the B bar, A and B. This portion is A and B bar. Okay, then the combine, you get an A. Okay, one more question. This one is for Leo. We have a set A and a set AB. Which one is bigger? A is bigger. We have a AB and a set ABC. Which one is bigger?
AB.
AB is bigger. Okay. So this one is very important, is that you have 1 letter, 2 letter, 3 letter. A should contain B. A should contain AB. AB should contain ABC. More letter means the smaller set. Fewer letter means larger set. Okay, let's assume that you have A means smart. So A set is smart people. B set is beautiful. So A, B set is smart and beautiful. So smart people, of course, more than smart and beautiful people. Because smart and beautiful people are more selective than smart people. Is that okay?
Yeah.
That's very easy to understand, okay? So when you have A, B, C, D, E, F, G, more term, then that's more selective. And the set would be smaller. Fewer term means it's actually a bigger one, okay? Next one, we have A or B and A or B bar. This one, you can use the distributive law, so you can do A or B and B bar. B and B bar cannot happen, so this one actually is 0. So A or 0 is still A by derivation, okay? You can pull that. This whole thing equals A. Now let's look at the Venn diagram, using Venn diagram to prove it. Venn diagram, you have A, you have B. So A or B is the whole thing. So A or B bar is A portion or B bar is outside, is right here. So A or B bar is anything outside here, anything right here. So the red one and yellow dash are actually the overlap should be this portion. This can pull that A or B, and the A or B bar is A. So far, okay?
Yeah.
Okay, so you got to write this different. So basically, you later, when you do if whatever the things and whatever things and whatever things together, they are very complicated logic. We teach you this Boolean algebra because we want you to basically simplify the whole complicated condition to a simple term, if possible. This calls logic simplification. Okay, so that's the purpose of doing all of these. Okay, next one we have the so-called redundancy rule. So A or AB, A or BB, we already talked about it. AB is smaller than A, is inside A, no matter what, AB is inside A. So A or AB is equals A because A is a bigger set. A and A or B is a bigger set. A is inside the A or B. So when two end, we pick the smaller one. That's A set is the A. So this is a redundant rule, okay? So that means that you end another smaller term is of no use. You or a bigger term is, you end a bigger term is of no use. You or a smaller term is also of no use. That's what this one say, redundant rule. A or 0 is A. You or nothing, you are yourself. You end nothing, you become nothing. Okay, 0. This rule are easy. 1 plus everything is 1. Because 1 is everything. 1 or anything is 1. 1 and anything is anything. Okay, these simple rules. Next one, A or A bar equals 1. This is simple. You A or A bar is in a unity. The whole thing is into 1. A and the A bar, A and A bar no intersection, so it's 0. Okay. So far, these are different rules. We may need it later to simplify it. Okay. Next one, we have A or A bar B. A or A bar B, you have A or A bar B. A bar B is this quotient. So A or A bar B equals A or B. Okay. A or A bar B is equal to A bar B. The next one is actually A and A bar or B. A bar or B. A bar, A is right here, B is right here. A bar is anything outside A. Or B, you actually need to add something in B but not in A bar, so it's right here. So this quotient is called A. This A bar B is A B bar. I'm sorry. A bar. Let me check one more. Okay, this one is this. We have to cover over this. Okay, then sorry. A bar or B and the A. Okay, I'm sorry. I almost lost it. A bar or B. A bar or B. A bar is outside. B or B is right here. B is right here. So it actually is this one. So this one and the A, this one and the A is only this part, and the A is only this part. So it's equals AB. Okay. But if you use a distribution law, you have an A and the A bar, or A and B. So this one is 0, so plus AB, it would be equals B. If you do simplification by derivation. Okay? Any questions so far? So you need to go through every single law by yourself and also derive them, also using this different way to prove them by yourself at least once, okay? Because you need that. Otherwise, later you cannot operate them. Next one is De Morgan rule, okay? We will focus on De Morgan rule and we will have a break after De Morgan rule, okay? De Morgan rule was saying two things. Let's go to the slides. De Morgan rule said A or B bar equals A bar and B bar. Okay, how to understand it? You have A or B bar is outside of these. A or B bar, not in A and not in B. So A bar or B bar is not in A. And then not in B. So not in A and not B is not in either A or B. These two are the same. Okay, by Venn diagram is the same. Now, if you want to simplify to remember how to calculate it quickly, okay, this one is very important. This De Morgan rules way to operate it is A or B bar. Number one, you break the bar, change the or to end. Break the bar, change the or to end. This will become this is De Morgan rule. Vice versa, if you want to combine A bar and then B bar, you actually connect the bar, change the operator from end to or. Okay, so De Morgan rule is either way. Break the bar, change the or to end, or connect the bar, change the end to back to or. Okay, this is the first rule. Second rule, you have A and the B bar will be equals A bar or B bar. How to operate? Same thing, you actually break the bar, change the end to or. So this one is A and the B's bar, and B's bar is this portion. And the A bar or B bar, A bar is outside A. B bar is outside B. So it's just not this old part. Okay, it's the same. Okay, so you can look at it. Any questions so far?
No.
So same thing, when you want to combine them together, you actually connect the bar, change the end to or to end. Okay, let's look at this. Okay, so let's look at this one actually. Stanford admission. You either you are a football player or you have high GPA. Okay, you can be a high GPA person or you are athletic, you are actually a football player. Either way, you have got admitted to Stanford. Now you are not Stanford admitted because you are not a football player and you don't have high GPA. So this is how we use the so-called De Morgan rule. Okay. Okay, another one does actually have a good boyfriend is smart and rich. Okay, I'm sorry, don't use smart, let's use a handsome. So a good boyfriend is a handsome and rich. Okay, but not a good boyfriend is not handsome or not rich. Okay, so your criteria to select a good boyfriend must be handsome and rich. But if a person is not handsome or he's not rich, then he's not a good candidate for your boyfriend. Is okay? This is I just pick it as an example to talk about what is De Morgan rules. Okay. Any questions so far?
No.
So far these are math. So we will have a break, come back on 9 o'clock. But during the break, please work on these different rules. Okay. Draw some diagram, try to understand it. This is a little bit abstractive. Okay. too abstract, so you need to use time to digest, okay? Keep my diagram on the, I'm gonna keep my screen on this 10 basic algebra laws. Okay, come back on 9 o'clock, okay? We will look at the examples, okay? Right now we are working on the algebra laws. We are not talking about XYZ at all, okay? Not real examples, okay? Come back later. Hello,
Hello?
any questions so far?
No.
No? Okay, so we cover the basic arithmetic rules. As you can see today, this topic is more like mathematics, less programming, okay? But we don't teach this kind of the Boolean algebra in a computer science principle course. That's actually too much for them, okay? But in CSA, these are needed because you guys are moving for more advanced programming, so it's needed, okay? Another thing we would like to cover is there's another symbol called, sometime in the set, there's another symbol called A minus B, the difference of the two set, okay? A minus B means that in A set but not in B set. So this one is equivalent to AB bar. In A but not in B. In A but not in B, it actually is this portion. Okay, it's called A minus B. Okay, in A set but not in B set. Okay. So these are something you need to remember. Okay, let's continue. Before we go into this logic function, let's actually look at something else. Let's look at this De Morgan rule. Okay, this one, the example, De Morgan rule. So usually this kind of set theory, you actually sometimes when you look at the multiple of something, it's very easy to understand. Okay. If this one, if x is multiple, is not multiple of 5, and x is not multiple of 2, and okay, both of it. So this one is A bar and B bar. Okay, it will be equivalent to A or B's bar. So it's x take modular by 5 equals 0, or x take 2 equals 0's bar. Okay, you equivalent to this is called De Morgan rule. Okay, so it's not multiple of 2 or 5. Okay. Now let's look at this Boolean quiz. I will look at it from internet. Let's see this one. I'm not sure this one okay or not. This is easy one. No, this one. Okay, these are different practices. Okay, like this one, you can practice it, okay? Here, I think it's a Python program or something. This one is a Python program, but you can actually work on this one, okay? It's actually a good activity for practice. Okay, I'm not going to work on this one, it's take too much time and. But anyway, you need to find some practice set on the internet to work on it, okay? Anyway, let's go back to here, okay? This one is logic design. Okay, let's go to this set theory first. So go to this set theory. So you declare Boolean m phi equals n modular phi equals 0. So when this is true, then the set of available numbers that would make it true, we call this m phi set. It's a 0, 5, 10, 15, 20. This is the multiple of the phi. We get m phi. So you declare that this m phi equals x modular x equals 0, then x in the set phi will make it true. Anything else will make it false. M2 is the multiple of 2. So when we say m and m2 and m phi is actually m s2 intersect with s phi, it actually is equivalent to m10 multiple of 10. M2 or M phi is actually the union of S phi and S2 is like this. Okay, and M2 and not M phi is actually is S2 minus S phi. M2 not M phi not M2 is this. M2 cap is inclusive OR. Means in one of the set but not in both. Okay, in one of the set, so basically anything multiple of 10 is deleted. You can say it actually equivalent to M2 minus M10 or M5 minus M10. Okay, you can think about it in that way. But anyway, this is the basic set theory and logic, okay? A Boolean condition always has a set that actually qualifies it. And those set after the Boolean operation will have the set operation as well to be true. Okay, that's what we say right here. Okay, then let's go back to the logic design. So the GPA course problem, you can say if m greater equals 90, you get grade equals A, greater equals 80, you say B, okay, and then C, D, F. But you cannot say less than 60 equals F. These two are not equivalent. Because mass greater than 90 is this portion, it says A is fine. Else, this portion is B is fine, okay? But if you say if m greater equals 60, you assign it to be D, then the whole thing here assigned to D, then you are in big trouble. So this doesn't work. Okay, this doesn't work. You can assign it else if it's not good. But if you take the else out, then that's probably fine. You take the else out, it's probably fine because you are going to override the D with C, so that will be fine. Is that okay? Is that okay?
Yeah.
Yeah.
So when you do math, you need to be careful, okay? Sometimes you can use and, sometimes you can take out the and part is okay, but sometimes the order also matters. You got to be careful, not the same. So when diagram here, you have the A, not, this is A minus B. In A, but not in B, this is A minus B, this quotient, okay? Sometimes it's also write as A slash B. This part B slash A, or B minus A, this quotient. And here A and B is A and B. A or B is A plus B. Okay, these are different symbols. So you have a set 0 is the nothing, 1 is everything, A is inside A bar is outside A over B is A over B both. AB is the intersection. A equals C or B is either in A or in B, but not in both. Okay? So this one, sometimes we use A cap B, A not equals B. Okay? These are the logic sometimes we use. Okay, so two Boolean variable you would have xy, okay, you have xy. So your xy might have a combination of 0, 0, 0, 1, 1, 0, 1, 1. Okay, so two Boolean variable, you have 4 possible combinations. Each combination have different logic value. So you will end up to have 2 to the power 4, that's 16 possible Boolean functions. So here we list down all 16 different Boolean functions from f0 equal false. This is f0. f1 equals x and y. That's actually when you have both 1 here, you have 1. So these are 16 different Boolean functions to implement all possibility of a Boolean function. So you have a x, y, f of xy equals something. And now generate 16 different combination of the function. We call it all the 16 Boolean function that can be expressed by x, y, and or, and exclamation mark. So it totally 2 to the power 4 possible functions. So these different Boolean functions we are used to do logic design. These functions also have a name. Okay, also a name. Commonly see the function is this one and or named then gate. Okay, no gate equals 0. These are different commonly see function name. Okay. There is a theorem called duality theorem. Duality theorem means that when your AB plus N equals 1, 0 is valid, then your AB and or equals 0, 1 is also valid. So AB plus A equals A, then this number system, you change it to A or B, and change to or change to end. The rule will still be true. It's called duality rule. Okay. This one is more advanced because 0, 1, 0 or 1 is symmetric. Okay. 0 or 1 is symmetric. In a way, from here you see a 1, here you see the 0 structure. 0 or 1 structure is the same, or and n is opposite. So you change the operator and the numbers, the rule should still hold. Okay, this is called duality rules. Anyway, these are two advanced. We just cover it a little bit. So these are different functions, 16 different functions. We say that is 2 to the power 4. 16 different functions name. Totally contradiction, 0 is contradiction, 1 is tautology, okay, and other name of the functions. Sometimes the set can be inclusive set, such as male and female. So it's impossible that you have the two set that have intersection, okay? Even though biologically may possibly have someone who is both male and female, but let's think about the general case. It's usually don't happen that way, okay? You have either you are male or you are female. Okay. And sometimes you can do number line analysis for the set as well. Okay, this one just talking about the set. And sometimes the definition of the logic set also matters. So right here you have if A equals 3 or X equals 4, that's A set. Okay, A set. If you define it in integer, this is true. Okay, this is true integer. And B set is A greater equals 3 and X less than equals 4, that's B set. Okay, so if X is an integer, then A set equivalent to B set. But if it's double set, then A, B set are not different. Okay, so logic rule, whether it hold or not, sometimes also dependent on the data type of the X. Is that okay?
Yeah.
If they are integer, they are the same. If they are double, they are not the same. So be careful. Now that means that always true when you talk about it. Okay, next one we will look into the compound logic. Before we do compound logic, let's actually let's see. Okay, let's look at the compound logic. We are going to write program now. Okay, given the integer n, we are going to check if n is a even number or not. So if n divided by 2, okay, remainder is 0, then we will return true, else we will return false. But this is not a good program, okay? Usually when you do the coding back, they'll tell you this you may not have returned outside the if. Okay, you may see that because when they do testing, they'll check if you have the full coverage of the different n, okay, conditions. So this one usually is not a good way to write it. Sometimes we just write as we take this one out. Okay, we take this one out. Okay. Because it's not needed. So right here, let's call it is even 2, okay? And then this one, we actually don't like it because we don't want it to write that long. When you just have one statement, you don't need to have a curly brace. If just one statement, you don't need a curly brace. So you write this one is good enough. Okay. Next one, you actually still don't like it. Because this one, we have the if A return true, else return false. So your duplicated logic. So basically this one, we kind of don't like it. You just need to return it right away. So be simple, don't write something too complicated. You actually just need this. And the parenthesis is not needed, you just need this one. Okay, this is it's even checking. Okay, this one we don't test it. Okay, it's easy. It's just give it there. Now this one. Next one we are going to check combinations. So we may have a public static integer array A equals 1, 2, 3, 4, 5, 6. Okay, let's go up to 6, okay? And then we have public static integer array B equals 2, 4, 6, 8, and okay. We have public static integer array C equals 1, 3, 5, 7, 9. Okay, it's actually a C array. Now we may want to check if the number are all evens. Given the array X, we check if it's all even. For doing this, we go using for loop. Okay, we check individual one. If one of them is not even, so here actually let's do this. Not even. So if X of I take modulo by 2, okay, not equals 0, it's not even, then we return false. Any of the odd number will call it to be false. So this is when we take all evens, we use this kind of logic. Otherwise, we get out of the loop and then it actually will return true. Okay. Okay, this one will check if A is all even or not. Because A is 1, 2, 3, 4, 5, 6, so some of them are odd. Okay, this is all even. Any questions so far?
No.
Okay, now next one actually, if we want to check all R's, okay, all R you actually will copy and paste. Okay, let's look at this one, OR. So this one, if there is an even one, then you will actually report false. Okay, so A have R have even, so it's OR or even both wrong. Okay, so next one we are going to test another one that's called public static, okay, Boolean has even. See if an array has any even number. So this one, you use a positive logic. Okay, this one you use a positive logic because if you see anyone that is even, then you return true. Else you return false. I also write down the has even and has odd, okay? Save time. Copy this one. So far, okay. So both has odd and have even, okay? Once you hit a even or you have an odd, your report is actually true. Okay, this is has even. You check everyone, there's a true, that is true. Okay. This one, all even or all odd, actually you say all, then if there's something not even, then you will actually report is false. Okay. Any questions so far?
No.
Okay, then we are going to do the version 2. Version 2, we copy this whole thing. Put it right here. Okay, so we are going to do all even number 2, all odd number 2, has even number 2, has odd number 2. Okay, 4 different way of implementing it. So now all evens also means doesn't have odd. So return not has odd. All odd also equals to don't have even. Has even also means not all odd. Has odd also means not all even. Okay, Lisa, you have to actually remember them, okay? So these 4, we are going to copy. And then I'm going to change the logic function name to version 2. That's it. Go. Okay, to deliver the same result, but label 2 have even 2 is defined by has odd, not has odd. All become so basically in mathematics we write it in this way. For all x belong to even. Okay, when you do negation, that means it is x, right? And then x doesn't belong to even. That means it is x in R. These two are equivalent. Is okay? This one is A's vertical down. It's actually called all. For all x, okay. This is E, but write it in the opposite way, means exist. So for all x, x is even. This one's negation equivalent to exist some x that's not in even. And that means that exist x that's in R. Is that okay? Can you understand it or no?
Yes.
This is symbol is ALL, but it's A, but it's actually vertically flip. Okay. This E is exist, is a horizontally flip of E. Okay. Now let's look at another one. Actually exist x not even. Okay. Exist some x that's not even. This negation would be all x actually is even. So these are the so-called algebra, compound algebra. We actually given any x, the rule should hold. So when we study algebra, we are exploring this kind of mathematical structures. Okay, we're studying the mathematical structure. When there's a compound behavior, we still with true or false. Okay, these are the compound structures. That's we are starting right now. Okay, and then so what this chapter is we starting from the basic Boolean rules, and then we talk about the transformation of these different basic rules, and then we go into the set theory to talk about what would make the logic true or false. And then we talk about the compound behavior of the all even, all are, those kind of things. So we do it step by step, okay? If you don't fully understand, what you should do is after class, you should write everything by yourself. Okay, that's the only thing that I can think about. Okay, so right here, let's actually copy this whole thing. Let's actually pass over here. So we are going to change A to B, okay? Since we have A, B, C, so let's actually change all A to B. So B, 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 B. Then we can check the B array. B array is all even, okay? It's all even. We'll check all the property again using the same function. Okay, then let's actually do it one more time. We're going to change A to C as well. C is all R. This one is very important, okay? When you do the multiple choice or the FRQ in the AP exam, they usually would test you this concept of all true or all false problems, okay? Has true, has false problems. So A is some are, some even, okay? So has R had even true, or are all even wrong. B is all even, so all even true has even true, all R has R false. C is actually all R, so has R and all R true, all even false, all even has even false. Okay? Any questions so far?
No.
So this chapter, you need to, number one, know how to simplify the logic. Number two, you need to actually be able to apply this logic into array or a compound conditions. When you combine multiple numbers, okay, whether it's true or not, okay? Now we have some more time. Let's work on the project, okay? I'm going to work on the project. This project is the leap year, okay, leap year, calendar leap years. So there's a question of the leap year, and currently we are using this Gregorian calendar. Okay, Gregorian calendar actually, wait. Number one, why we need the leap years? Jiang, why we need leap years?
Oh,
Why we need leap years?
wait, what do you mean? Can you say it again?
Why we have leap years?
Oh, because 1 year is not exactly 365 days, but it has a little like more hours. So we have one extra day on February to make that up.
Okay, that's great. So basically, your Earth go around the sun is not exactly 355 days. So in the early days, maybe 5,000 years ago, people observe that and then they think that, oh, 1 year is 360 days. So they say that the circle we mark every day, they are 360 degrees. Okay, that's actually where it gets started. So when you study the sundial, we actually have a homework, right? Working on the sundial. And they tell you that actually each degree, inside the degree is also minutes. Inside the minutes, they are still what? Seconds. You remember that problem? Maybe problem 8 in some of the homework. Remember that? Is that okay? So that's the origin of the degree, second, and minutes come from, okay? It's actually related to time, but in the old days, actually 360 is used because the circle got marked by 360, but it's not really that many days. It is 365.23 something, something, something. So if every 4 years, we compensate for 1 day, then this is 23 maybe become 96 or something. So basically every 100 years, your leap day is too many, so you need to minus 1 day. But another 400 years, you actually not enough. You need to make up for 1 day again. So that's actually the rule of the leap year. Is that our calendar is quantum, is actually numerical, is by numbers. But your sun go around the Earth go around the sun is not exactly 355 days. So how many days exactly for Earth go around the sun? So it's roughly 265.25, actually not 25, 23 something, 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 okay? You can check the website to search for the exact numbers, but here we are not discussing it. We just want to tell you that's the reason. Oh, I'm sorry, actually is it actually is 365.256 something. Okay, I don't know, but you can study it. Okay, here we don't actually calculate the exact date and time for it. Okay, anyway, that's where it come from. Okay. So now the question is why the Chinese want to use the zodiac of the 12 different zodiac symbols. Anybody know? Why you have the red ear, you have the ox ear, you have tiger ear, you have rabbit ear, you have dragon ear, you have snake ear. Anybody know? Anybody know? So 365 days is the number of the days that Earth go around the sun. But why we have those different zodiac stuff? Anybody know? How about you? Do you know?
Oh no.
That's because your sun is over here, your Earth over here, your Jupiter. Jupiter is outside. Okay, Jupiter is outside. Jupiter go around the sun by 11.87 years, so roughly 12 years. So every 12 years, you will see Jupiter show up on the orbit of somewhere. So in certain section, we will say it is red years. In certain section, we will say it's ox year. So these are years of these actually is by the so-called position of the year Jupiter. Okay, that's a planet of the years. It's actually Jupiter go around the sun every 11.87 years. Okay, so that's zodiac. Okay, so this kind of zodiac things, and we actually have leap year calculation. We have the zodiac symbol calculation, and use a lot of modulus. Okay, use a lot of modulus. Now let's look at the leap year calculation. Okay, so leap year calculation, we have a leap year. Okay, given a year, we would like to check if it is a leap year or not. Okay. So if the year actually is multiple of 400, then we will return true, right? So any M400 is true. Okay, so anything after this not M400, right? For sure it's not M400. So we will say if y 10 multiplied by 100, then we'll return false. That's for sure, because right here is no longer multiple of 100. So actually, this one M100 is false, for sure. So right here is not M400 and not M100. Okay? Then you say if y 10 multiplied by 4 equals 0, you return true. This one is M4, right? Otherwise, return false. Right? This is version number 1. Actually, just by the logic, you code it in this way. But this is no good, okay? This is no good. It's no good because let's look at version number 2. Version number 2, because this one you have if A return true, else return false structure. So right here, you directly return this is enough. Okay, the version number 2. Version number 3. Okay, we further reduce it. Since 100, you are going to return false. So this one you have not 100 and the 100. 100 you return false. Not 100 you check is actually M4 or not M4. Yes, M4 is true, this one is false. Okay, so you will be true only if you are 104, not 104. This is true. Other cases are false. So these two can be combined. So these two can be combined. You just return not actually yt multiplied by 100 not equal 0 and yt multiplied by 4 equal 0. Not n100 but also n4. Only this will be true. This is not to replace it. Okay? And then this one we can further reduce it. For the version 4. So right here you have the N400, N not 400, N not 400, you have N100, and not N100. So this one is true, this one is false. This one you have N4, that's true, not N4, that's false. So you are true in this case and in this case. Okay? So with that, we actually can further simplify it to return, okay, yt multiplied by 400 for 0, or that's the first case. Second case right here is actually yt multiplied by 100 not equals 0, and yt multiplied by 4 equals 0. That's it. That actually is the most simplified version of the linear calculation. Let's go. Okay, from 1900 to now, okay? So it's a year percentage B is a leap year, is percentage B backslash N Y, and then is leap year. Let's use a version 4, okay? We don't check other function, you can check by yourself. Go. Okay. Is that okay so far?
Yeah.
1900 is not, okay? It's actually the multiple of 100, but not multiple of 400, okay? So these are the program to check it. This is the library we have. Okay, so that's actually our project today. This one, the zodiac year, we already show you how to do it last time, okay? We already show you how to do that. And then sometime later, we'll tell you how to bring the calendar report, okay? The whole calendar. Not right now, okay? When we teach you the loops, we'll teach you that. We teach you the leap year and the no leap year. Last time we talk about how to calculate the no leap year, okay? So these are something we covered so far. Any questions so far?
No.
No.
Any question about the homework?
No.
Okay, I'm sorry that yesterday I cannot host the coding practice, okay? So you want to make up next Monday and next Thursday, you can still come in at 8 p.m. Pacific time. That would be noon time or your certain date, okay? That's the only time that I can make up. Okay?
Okay. Okay, thank you.
That's it for today, and work hard, okay? Right now it's very hard. We talk about this theory because the programming to get harder, you need to study it, okay? So if you missing something in math, what you should do is you still go to the Khan Academy for set theory. Okay. So Khan Academy had a good course of the set theory about which union what, okay? If you don't know about the union intersection, those kind of things. Or if you don't know about Boolean algebra, same thing, okay? I think it actually is the best source, free, and also have many practice problems. You should go here. Boolean's logic if statement. Let me see, compound Boolean logic operator. Okay, is that okay?
Yep.
Work on this one if possible, okay? Don't just watch the video or whatever, it's not enough. You have to deal with the Boolean algebra, with the logic operator, these different kind of problems, okay? We cannot give you enough practice because we have limited time, okay, and space. But if you want to dig deeper into there, you should go here, okay? This one's AP College Computer Science series, okay? Come to here to do it, okay? Okay, good night and wish you good luck, okay? Good night, bye-bye.
Wait, I have a
Yeah.
question about the homework.
Yes,
So,
okay,
you know, like the exercises, it says you have to assume that Z is 23 or something. The first question is exclamation mark GUS. What am I supposed to do for that problem?
you're talking about exercise.
Yeah.
Let's see, okay, one moment, okay?
Okay.
Now we bring up the homework. Which chapter are you talking about?
Today's homework. So chapter 7, I think.
Number one, don't do homework during the class, okay?
I didn't. I just opened it because I was going to do it after class.
Yeah, you're not supposed to do it in the class.
Yeah, I did it.
You did it before.
I didn't. What?
Yeah, you actually usually submit the homework right after class.
Yeah, I submitted right after because
So I just tell you not to do it, okay?
Okay.
Pay attention to the class, that's number one. So you're talking about this one. Let me see what problem it is, okay? Which problem you're talking about?
First one.
First one, given these different numbers, and then which question you have?
Number one, like what is
I'll check, okay? I'll check. I think this one is a misspell somehow.
so are we supposed to like put the variables into the program and then print those things out? Or like in a text file and put the answer?
You write your answer.
In a text file?
Yeah, in a text file. Yeah.
Okay.
You run the program is fine. Either way, you'll figure out an answer. But here, I think we want to test your understanding of the program.
Okay. So just
Okay.
text.
So this one maybe not typed well. It actually double equal sign. Okay.
So
This one is
wait.
double equal sign.
Oh, okay.
Okay, I'll check this GUS what that is. I think it's somewhere maybe this one and this one maybe end or something. Okay.
Okay. Okay.
I
Thank
think
you.
it's a mistype problem. I'll modify the program as it's wrong. Okay.
Okay. Thank you.
Yeah. Okay, so this one actually give you more exercise of the logic. Okay.
Yeah.
Yeah. Try not to work on it in the during class time. Okay, it's not a good bad
Okay.
habit.
Okay.
Good night. Bye bye.
All right. Thank you. Bye.
Alright,
Thank you.
Bye bye.
thank you.